Welcome to session 7 of the Keck Science meeting. We have an assortment of talks for you today. The first one is by Christina Vides, who is a graduate student at UC Irvine. So Christina is going to tell us about a multi-wavelength study of the V892 tau circumbinary disk. So Christina, whenever you're ready, take it away.
Screen. There you go. Thank you. All right, thanks, Steph, for the introduction. Like you said, hi, I'm Christina Vides, and I'm going with my third year of graduate school at the University of California, Irvine, where I work with Steph Salem and our wonderful collaborators. And today I will be talking about new constraints on the geometry of the V892 tau circumbinary disk. So what is a circumbinary disk? Well, let me begin with what a circumbinary planet is. A circumbinary planet is a planet that orbits two stars. This is typically known as a p-type orbit, as opposed to an s-type orbit, where the planet orbits one star in a binary pair. The first circumbinary planet was discovered in 1993 around a millisecond pulsar and a white dwarf. And in 2005, the first planet around a main sequence pair was detected. But only a handful of circumbinary planets have been detected. Kepler found about 10 circumbinary planets and even fewer planets in the S-type orbital configuration. So in order to, this may be due to a detection bias or orbital stability in these systems is short-lived. But we can use circumbinary disk detections to study the conditions that form planets in these configurations. V892 tau is one of these stars with a circumbinary disk. It is a young AE star located 135 parsecs away in the Taurus-Auriga star-forming region. It is an A-type star, and the total mass of the system is about six solar masses. The circumbinary disk was first discovered when it was imaged at 10.7 microns, and about 6 months later, it was imaged at K-band, and the stellar companion was resolved. We show a toy model of the system as we know today. The diameter of the disk is about 26 AU. In addition to the initial discovery, the stellar companion has also been resolved at K-band and in the millimeter continuum with ALMA. And there's N-band mini data that helps with constraining the circumstellar environment. But to us, V892 tau is one object in a 30-object survey that will form the basis of my PhD thesis. We aim to constrain planet formation by placing statistical constraints and imaging protoplanetary disks with non-redundant masking. So what is this non-redundant masking that I mentioned? Well, non-redundant masking, or NRM, is an aperture masking technique in which we can turn a conventional telescope into an interferometric array. We do this by placing a mask in the pupil plane of the telescope, and similar to the one shown here. What makes this mask non-redundant is no two poles have the same orientation or separation, so each baseline or pair of poles has a unique spatial frequency associated with it. We see the interferogram on the detector, which is the middle panel, and we can take the Fourier transform of the interferogram and calculate two observables from that. The first observable we're concerned with is the squared visibilities, which is the real part of Fourier transform squared. And the second observable that we're concerned with is the closure phases, which is the sum of the Fourier phases around baselines that form a triangle. What makes this technique so powerful and why we would want to use this to image protoplanetary disks is one, closure phases are highly sensitive to asymmetries, and two, non-redundant masking provides moderate contrast at angular separations down to and within the diffraction limit. So we use the non-redundant mask on Keck-2 to observe V892 tau with NERC2. We first imaged it at L-band in November of 2020. And we chose L-band because that's where newly forming planets are the brightest. And we followed it up at K-band in January 2022. We chose to image it at K-band because we really wanted to be certain that we were differentiating the disk emission from the stellar companion emission. We show our UV coverage for the night, or the in the top panels, or the rotation of each baseline pair with parallactic angle throughout the night. We had about 64 degrees of sky rotation at L band and 108 degrees at K band. We had a total integration time of 40 minutes for L band and 30 minutes for K band. But what makes these two observations very unique is they are among the some of the first observations to use non-redundant masking in conjunction with the pyramid wavefront sensor. So we take our two observables, our closure phases and our squared visibilities, and we use those to reconstruct the images, which are shown here in the bottom panels. These the primary star, the starlight from the primary star is suppressed and marked with these plus signs. We then model our data by fitting geometric models to the two observables. We found that a Gaussian disk and with two delta functions is the best model for both the L band and K band. I'll focus on the L band data first. We resolved a circumbinary, we detected a circumbinary disk and the stellar companion. Since the stellar companion is represented as a delta function, it is circled right here. One striking feature about the disk is that the skew of the disk is oriented along the position angle of the companion. This may be due to heating of the disk by the companion, and this is seen repeatedly in the literature. Now, focusing on the K-band data, we detected a circumprimary disk. So the disk is only around the primary, and it's about 1.6 AU. And the separation between the primary and the secondary is about 5 AU. So similarly to the L-band data, the skew of the disk is oriented in the direction of the along the position angle of the companion. But we cannot be certain if this is a physical feature of the disk or if this is a degeneracy in between skew and contrast in our model fitting. We explored a variety of different models to ensure that we had the best fit. We fit just a binary, just a disk, and the binary plus disk to our closure phases, which are shown in the left as a function of maximum baseline in the closing triangle, and the squared visibilities as a function of baseline. We found that the disk plus companion fit had the lowest chi-squared value out of these different models, and the data was best correlated. We show our correlated data against our model, and we show that that's very well correlated. We repeated this for K-band. However, we did find that the circumbinary disk was the best model, but to ensure that we weren't getting stuck in some local minima, we set our prior on our model to ensure that the companion would always be within the disk. And so we forced a circumbinary disk. And when we looked at the best fit model in posterior distribution, we found that there was no flux in the disk. So we did not detect a circumbinary disk at K-band. So we used our model closure phases and our model squared visibilities, and we wanted to see if we could get the initial observation back. So we used our simulated best fit observables to reproduce the reconstructed images from the data. We then used our astrometry along with the previous points to the previous K-band and all points to update the orbit of V892 tau, and as indicated by the color bar, the orbital period of the system is about 7 years, and the semi-major axis is 7 AU. And here we show the 50 random orbits sampled from our posterior distribution. So how does this all compare to previous results? Well, one, our data is in photometric agreement with previous results, where more of the flux from the disk being emitted along the position angle of the companion. We detect a circumprimary disk, which is consistent with the MIDI data, since they found that a circumprimary plus circumbinary disk best to describe their data. However, they were still very inconclusive with their results and suggested more K-band data. So we update the geometry of the V892 tau system. We also constrained the orbital parameters of the system, and we found that our error bars are 10 times smaller than previous estimates, which are shown in this table to the right. In addition, we also place contrast limits on undetected companions. We show our contrast curves for L band and K band, and we compare our magnitudes to magnitudes predicted by hot start models, and we find that we're sensitive to 20 Jupiter mass planets at L band and 50 Jupiter mass planets at K band. So we place upper limits on the planetary masses in the V892 tau system. We also find that we're sensitive to rapidly accreting giant planets, and we find that at L band, we are sensitive to very rapidly accreting Jupiter analogs and slightly less rapidly accreting 10 Jupiter mass planets. We also compare our contrast to, we also characterize RAO performance for the night, and we compare our contrast to contrast curves from Shack-Hartman data, or from data with Shack-Hartman wavefront sensor. And we find that with the pyramid wavefront sensor, we can achieve contrast about 0.5 to 1 magnitudes better. So in summary, we have the first detection of a circumprimary disk, about 1.68 U in diameter. We improved the orbital parameter uncertainties by a factor of 10, and we placed contrast limits on undetected companions and characterized the AO performance of the first NRM and Keck pyramid wavefront sensor data. We also want to stress the importance of multi-wavelength data, which allows us to be able to differentiate the disk emission from stellar emission. And with that, we'll take questions.
Okay, thanks, Christina. Let's see, checking the Slack, I don't see any questions there. Are there questions in the room?
Yeah, we've got 2 hands in the room. I've got Lynn and Bruce. I got Lynn go first.
So as I recall, V892 tau is the last one, is that right?
Yes, yeah.
That's a massive star, or maybe?
Yeah, it's a B or A type star. I didn't have a lot of time, and that's all they're talking about, whether it's a B or A type star. In the literature, it's still a little constrained.
And so this is a stellar companion.
The stellar companion, yes.
And then with regard to the disk, I guess it's a bit surprising that you see something that's kind of standoffish from the star, or extended from the star, as opposed to
So
going all the way in. This is, again, as I recall, this is more like an envelope.
right. So at L band, we detect an envelope around both stars, and that's consistent. That's been shown in literature. However, at K band, because our angular resolution is much higher, we are able to detect a disk around just the primary.
But it's not close to the star. It's not in at a 1/10 of an AU or something. That gap you see is really
Right. That gap is about like, yeah, it's a large gap. It's like a 12 AU gap. Yeah.
Thank you.
Okay, we actually have a question in the Slack. So since I'm a virtual chair, I will go over there for a second. Kyle Cabasares asks, he has a quick question on the geometric model fitting in comparison to previous results. The modeling is happening in the UV plane, is that right? And is this through chi-squared minimization or MCMC? And then he also asked about whether the error bars are statistical or systematic uncertainties.
Right. So, okay, we use MCMC to fit our data. So we're fitting our closure based up in our squared visibility. As far as error bars, so these are error bars that are calculated when we reduce our data. I'm a little unclear about your question, though.
Think of it as how do you estimate the error bars? What's your confidence in that those are the right error bars?
Yeah, so these are the error bars that are calculated by Yeah, from the MCMC.
Right, but there's error bars on the individual visibilities that must come out of the, like each visibility point there has a little error bar on it, that must come out of the NRM code, right?
Right, yeah. So those are just, yeah, those are systematic.
I know Bruce has a question too, but I think, is that our wrap up right there?
That's the timer.
That's the timer buzzer.
We'll chat later.
We'll
It's
chat.
really, really, really nice.
Thank you.